Here's a new example. Y double prime minus 7y prime plus 12y equals e to the 3x. So why is it new? Well, let's first get the characteristic equation, which is m squared minus 7m plus 12 equals to 0. And as usual, we set this up so factor m minus 3, m minus 4 equals to 0 is the factored form. And the roots are 3 and 4. So it means that the characteristic equation, the complementary solution, is going to be C1 e to the 3x plus C2 e to the 4x. And so now we see the problem, because the right-hand side of this equation is e to the 3x, and I already have e to the 3x in my complementary solution. So I just can't simply say, well, let y particular be a e to the 3x, and because we've already taken care of that right here. And matter of fact, this portion, or this portion, when we plug it into here, equals to 0, not e to the 3x. So there's the issue. When one of these roots appears up here, and somehow on that right-hand side, the q of x, then we have to do something different. And just one more time, I want to make sure you got this, because if I use this as my particular solution, when I plug this in here, you'll find that the whole left side canceled. You have 0 equals e to the 3x. It just simply doesn't work. So I have to do something different. Well, alright, so what do? It turns out that, I imagine they found this out through trial and error, whenever this first came up, that you could set up the particular solution, y particular, to be ax e to the 3x. In other words, we're going to step it up by multiplying by x. And so let's see if that works. The first derivative would be, and we have a product rule here, so it's going to be, this derivative times this. This derivative is a e to the 3x plus the derivative of e to the 3x times ax. That's 3a x e to the 3x. So there's our first derivative. And our second derivative will get even messier. So we have 3a e to the 3x plus 3a e to the 3x plus 3 times 3, 9a x e to the 3x. And we can combine the first two terms, so that becomes 6a e to the 3x plus 9a x e to the 3x. There we go. So now let's plug all this in and see what we can figure out. So my second derivative, y double prime, is this part. So I'll rewrite it: 6a e to the 3x plus 9a x e to the 3x minus 7 times my first derivative, so it's minus 7a e to the 3x minus 21a x e to the 3x, and then plus 12 times my function, my particular function, 12ax e to the 3x, and all this equals to e to the 3x. So now then, I can divide off the e to the 3x's, because it appears in every term, and e to the 3x is non-zero anyway, so we can safely divide by non-zero terms that are, so this gives us 6a plus 9ax minus 7a minus 21ax plus 12ax equals to 1. So I divided everything by e to the 3x. I just want to double check myself. 6a, 9ax minus 7a minus 21a x plus 12ax equals to 1. Alright, well let's gather up the terms here. I have 9a x plus 12ax is 21ax minus 21ax. Those cancel. Very convenient. Off the top of my head, I can't tell you that that's always going to happen. It's just not quite sure. But anyway, we have 6a minus 7a is negative a is 1. So a is going to be minus 1. So I can put a negative 1 here, and now we can write out the general solution, which I'll do next. So our general solution is going to be this. Y is equal to c1 e to the 3x plus c2 e to the 4x, complementary solution. A was negative 1, so the particular solution will be minus x e to the 3x. And as a finesse, we could combine the e to the x terms, c1 minus x, parentheses, e to the 3x, plus c2 e to the 4x. And now we're done.